And as a reminder, your final exam is Wednesday of this week. And please, if there are any, as you're studying, if there's any content or questions that come up, please let me or the TAs know. So today we'll talk about what I think is both a classical and simultaneously an emerging topic of organometallic chemistry and coordination chemistry, which is the photochemical properties and the reactivity that the unique reactivity that can be exploited in organic synthesis from photoexcitation of transition metal complexes. And so we'll start out trying to sort of dig into some of the details of what I think is the most classical and probably earliest example of a photochemically promoted reaction in transition metal chemistry, which is the photochemical dissociation of ancillary ligands, namely in this case, most commonly CO. And then we'll talk about some of the photoinduced electron transfer properties that can be taken advantage of in transition metal chemistry and catalysis, including some more recent developments in what's now sort of been coined photoredox catalysis. And then, time permitting, we'll talk about a few sort of related examples from the recent literature that are not necessarily photoredox in nature, but certainly are deeply connected to some of the other chemistry that we'll cover today. Okay, so one of the when we were learning about ligand exchange and that elementary step, we talked about how photochemical irradiation was a well-established strategy for promoting ligand dissociation. So we'll just unpack that a little bit and see how this relates to some of the chemistry that you see, I guess, more commonly in the literature these days. And so I'll begin this talk by introducing some of the sort of tools of the trade in photochemistry and photophysics of transition metal complexes and some of the nomenclature that's involved there. And then we'll talk about mechanistically the mechanistic origins of photodissociation and also preparatively how that can be useful in accessing different coordination complexes. So one of the ways in which photochemistry of transition metal complexes is depicted is using this this graphical depiction here, which is called a Jablonski diagram. So just in terms of the overall organization, not surprisingly, vertically things are organized from lowest energy at the bottom to highest energy at the top. And then going from left to right, the electronic states of the molecules and transitions involved are organized by the spin multiplicity of those complexes. And so this is sort of a Jablonski diagram for just an arbitrary transition metal complex. And so let's consider this case where there are two energetically accessible absorption bands. So one which is higher energy and has a smaller wavelength of light involved, and the other that's lower energy. And so there's some sort of alphabet soup here in terms of the depictions of the electron transfer steps that are involved. And there's actually on one of the handouts that you'll get, it sort of defines all of these, so you don't necessarily need to write these down. But MLCT refers to megan to metal to ligand charge transfer. And you'll also see the opposite, ligand to metal charge transfer, and other terms that I'll try to define as I go through. And if I miss anything, then please stop me. So let's consider this case where we have the high energy metal to ligand charge transfer driven by light. So an electron is excited from the ground state to now this excited state that's predominantly predominantly ligand based. Remember that essentially all orbitals of coordination complexes have both a metal and a ligand component. So what we're really saying here is that the orbital that's involved has predominantly ligand character in this case. So now a couple things can happen. So one is what's called internal conversion. It's a non-radiative process where this higher energy excited state can relax to still a high energy excited state, but now one that's slightly lower in energy. From here, the excited metal complex can undergo fluorescence, in which it's giving off a photon, or it can undergo intersystem crossing from a singlet state to a triplet state. And here too, there are some options. So from the triplet state, it can undergo internal conversion to a lower energy process. And from here, it can undergo phosphorescence. The key being phosphorescence is happening from a triplet state as opposed to a singlet state, which was the initial state of the excitation. So as we probably all learned in analytical chemistry, fluorescence is this process of going of a singlet to singlet conversion, and phosphorescence occurs after intersystem crossing. And as a result, this is typically a lower energy photon that's emitted. And also, I think I just want to highlight, without going into too many of the details, the connection between what we're going to cover today and the spectrochemical series, which, remember, was an empirically derived series sort of in the early days of coordination chemistry that defines the coordination strength, or rather the strength of the ligand field as a result of the structure, as a consequence of the structure of the ligands involved. So if you think back to that series, you'll remember that ligands like CO, for example, are strong field ligands. They result in complexes that have absorption energies that are large in nature. And so as it pertains to this, this class today, we'll see that, again, ligands that have these strong field ligands are absorbing relatively high energy light. And another term that's important to define is quantum yield, and this is quite a simple term that defines sort of the efficiency of the photochemical process, and is defined just as the number of molecules of product, or the number of molecules that undergo the desired transition, divided by the number of photons that are absorbed. And so one of the features that will recur again and again, and probably you've seen in many talks if you've attended lectures by folks working in modern photoredox catalysis, is that triplet states in general are longer lived. So triplet excited states are longer lived than singlet excited states, because the decay of a triplet excited state to the ground state is a spin-forbidden process. But when this is defined as longer lived, it's important to remember that it's still a very short-lived intermediate, and so the lifetimes, the range of lifetimes here are shown. And so as a result of these still in general being fleeting intermediates, historically bimolecular steps are often too slow. Of course, this is not always the case, but often the case, too slow to contribute. And so photodissociation is sort of the most common thing that can happen upon irradiation of a transition metal complex. So let's look at a few examples now of photodissociation and discuss, at least in a general qualitative sense, the orbitals and the nature of the excitation processes that are involved in these photodissociation processes. So let's consider a classical metal carbonyl complex, tungsten hexacarbonyl. And this, I think, this overall analysis will hold for any homoleptic metal carbonyl complexes. So it's known that if you just consider an arbitrary monodentate ligand and you're trying to do a selective dissociation or ligand exchange of one carbonyl for this monodentate L-type ligand, and you do that under thermal conditions, what you get, in fact, is a mess. Because it's very difficult under these elevated temperatures to control the number of CO ligands that are replaced by the L-type ligand, say a phosphine or a pyridine ligand. In contrast, under photoirradiation in the presence of what could be a stand-in ligand as solvent like THF, you can get smooth photodissociation of a single CO upon irradiation to make a tungsten pentacarbonyl THF complex. And so this part requires light, but if you have appropriate L-type ligand in solution, at that point you could turn the lights off, and this exchange ligand association will take place even in the dark. So it's a nice example of being able to get divergent product outcomes and actually improve product outcomes in this case in the presence of light.
What's the nature of this THF complex? How is it bonded?
I think that
what's the lifetime of it, I guess, as well?
so. Okay, let me answer your first question. I think the bonding is normally drawn just like this. And the lifetime, I'm not sure of. I don't have that written down. I think that it's certainly the THF is a labile ligand, so I imagine that it's not. Say it's not extremely long-lived. But I think you yourself have worked with this acetonitrile complex, and that's a stable solid.
Yeah.
And so, particularly for preparative applications, it's important in this type of experiment to have a knowledge ahead of time of the UV spectrum of the starting material, and also if they're known products that you might be making, because you could imagine if you're exciting at a particular wavelength and or a range of wavelengths, and you're hitting your starting material complex, but you're also hitting your product, then that product becomes an intermediate because that too will be photoexcited. You'll lose CO and coordinate another THF and undergo a double substitution. And so that seems quite obvious, but I think it is important to emphasize. And we'll talk a little bit about the mechanism here just in a minute, but just so that people are on the same page here and to see how this contrasts to other potential scenarios. Historically what was believed to happen here is that the electron that's getting excited is a non-bonding d electron, d pi electron, and that upon excitation it gets excited to a sigma symmetry metal ligand orbital that is at the anti-bonding sigma star level. And so that, as you might expect, would weaken the ML bond. And so the actual situation here is a little bit more complicated based on sort of modern computational work. But I think as a first heuristic, this is a useful way to think about it. And we'll get into that in just a minute. So here's another example where the underlying electron transfer processes are a little bit different, but the overall outcome is still quite similar. So if now you consider a tungsten tetracarbonyl phenanthroline complex, so I'll just draw that out in case anyone. Just to make sure everyone's on the same page. So here too, upon excitation with light, we can get selective monosubstitution with a phosphine ligand to get this product. But what's actually going on in terms of the electronics a little bit, the electron transfer is a little bit different. So in this case, it's believed that you see that there are two absorptions. So one is what's called a ligand field. So ligand field, or abbreviated LF, this refers to electron transfers that are d to d, so from one d orbital on the metal to another d orbital. And then there's another absorption in that absorption band that's consistent with the metal to ligand charge transfer. And so this is d, non-bonding d to pi star. In other words, an electron is transferred from the metal, which remember has non-bonding electrons on it, to this relatively low-lying pi star orbital of the metal, of the ligand. And so that's depicted in this formalism, where now the metal is drawn as a radical cation, and the ligand is drawn as a, I guess it should be a radical anion. Perhaps unsurprisingly, so yeah, the overall effect here is the same, but what's actually going on is a little bit different, and how this works hopefully will become clear in just a minute. As might be obvious intuitively, chelated ligands are much more photostable than monodentate. I think that's why a lot of the most popular metal-based photoredox catalysts have polydentate ligands on them, although that's not 100% always the case. Generally, that's true. And I think that the underlying origin of why that's the case is that upon excitation to, let's say, a sigma star orbital, then a polydentate ligand is able to occupy multiple axes of the metal, such that the sigma star is not always in their that ligand's orbital, so to speak. Okay, so now let's look at the mechanism of this first case that I mentioned, and look at this in terms of the orbital diagram that's involved. So a metal homoleptic carbonyl, hexacarbonyl complex will be octahedral, and so it's D6. Remember, we have a T2G symmetry orbital and an EG symmetry orbital. The T2G is non-bonding, and the EG is metal ligand sigma star in nature. So upon excitation, then we have a ligand field, D to D electron transfer, which results in excitation of a T2G to this antibonding orbital. So historically, I think this was the accepted model, and I've put some quantitative data here in terms of showing how big of an effect photoexcitation has on the rates of ligand exchange. So you see it's a phenomenal 16 orders of magnitude faster to do something like this with a phosphine ligand than without it. There's as folks have continued to look into this, in the case of the hexacarbonyl series, the picture has gotten a little bit more complex. So I think for the purposes of this class and for the purpose of understanding what to expect, I think this is a perfectly useful framework, but just to have a bit of a snapshot about the more complex picture that's emerging, I decided to just include a short blurb here. And so previously it was thought that the electron transfer was predominantly from the non-bonding d orbitals of the metal to the ML metal ligand sigma star. And various computational studies have shown that a more likely scenario is actually metal to ligand charge transfer to a pi star of the carbonyl. And then, as you might imagine, if, let's say, in this hexacarbonyl complex, one of these COs now is excited because a electron has been promoted to its pi star orbital, this becomes asymmetric, and we've learned previously that in this case you have Jahn-Teller distortion. Jahn-Teller distortion changes the relative energies of the orbitals involved to allow mixing of the otherwise higher LF orbital, LF state with the MLCT state, and as a result you get state mixing, and this populates the dissociative state of the CO ligand. So again, I think going in any further depth there would be outside the scope of this class, but just so that you know that these processes are quite mechanistically complex, and I think as years move, as the years pass, there are more details that are sort of layered into our understanding here. Okay, so are there any questions regarding this sort of primer into photochemistry of transition metal complexes?
How does the selectivity for dissociation change between using light and using like a chemical method of dissociating a CO, like an N oxide or something?
Yeah, that's a good question. So Stephen's pointing out that another way to activate a CO ligand for substitution that is common is treatment with a NO to generate CO2, which then dissociates. I would guess, without having some sort of clear case studies in my mind or on hand, I would guess that the photochemical method would be more chemoselective because the absorption properties of, let's say, a hexacarbonyl versus a pentacarbonyl will be quite distinct, whereas I think their relative rates of reactivity with an N oxide will be more similar. And so if I had to guess, I would say that photochemistry would be more selective. So the photochemistry of transition metal complexes is a massive topic, and so I could probably teach a whole class just on that alone. So hopefully I've done it a little bit of justice, but it is a big topic. So one of the major players in this area is our chemist of the day. I think everyone should have the handout. Raise your hand if you didn't get the handout yet. You guys did. Does anyone want to take a stab? Tanner, any thoughts?
It's really dark.
It didn't print out well.
Yeah. First,
Okay, this is Mark Crichton. Carried out his bachelor's studies at Florida State, PhD at Caltech with Harry Gray and Hammond from Hammond postulate fame. Earned his PhD at 22 in 1972, and then became a professor at MIT, where he rapidly rose through the ranks until 1995, and then moved to become the chancellor at WashU, and is credited for the explosive growth of WashU over the past 2 decades. Wendell MacArthur grant in 1972, and is known for photochemistry of transition metal complexes, obviously. Some of his famous students include the likes of Chad Merkin, and I think is an interesting example of someone who was highly successful in research and then also incredibly successful in his post-research career as an administrator. And actually, he's the chemist of the day because he literally wrote the most useful textbook on photochemistry of transition metals, which is part of the reading that's highlighted on the worksheet. And I think the first chapter of that will be in the Canvas for you to look at in case you have additional questions. So one of the complexes that Mark Wrighton studied in the early days is the famous homoleptic ruthenium 2 complex Rubpy. And so this is actually a very old coordination complex. It has a very rich history. So it was first reported in Burstall by Burstall already in 1936. And one of the things that he found already in this early study was that it could be resolved by tartrate and that it was configurationally stable. So it's an example of a chiral at metal complex. And then very little was done of this. I think that its full potential was not realized until 40 years later when folks like Brighton and others started digging into the photochemistry of how the excited state of this complex can be quenched by various organic compounds in solution. So we'll get into that shortly. And then there was still another sort of short lull from understanding the fundamental electron transfer properties to then being able to apply these in organic synthesis, which started to happen in the late 70s into the 90s, and then a renaissance in the late 2000s based on some high-profile papers by Dave McMillan, Teshik Yoon, and Corey Stevenson on using Rubpy along with co-catalytic strategies in the case of McMillan for alpha radical-based alpha functionalization of carbonyl compounds, 2+2 cycloadditions, Yoon, and reduction of alkyl halides in the case of Stevenson. Okay, so let's take a look at problem of the day number 1. So this asks how one might go about synthesizing Rubpy, and also about its electronic configuration. So the first question is, the first part of it is essentially a review, to start getting you primed for exam time, and then also thinking about how to make this, and particularly the salt shown, the PF6 salt. Okay, how about for part A, Vincent, can you help us with this?
Sure. Oxidation state is 2. The electron count is 6. And overall electron count is is 18.
Anybody get anything different? Okay, what about the synthesis? Tejo, what do you think?
Not sure, but I think just can bipyridine, excess amount of bipyridine to proceed.
Okay, that's a good initial thought. So, Tejo's saying, let's just do this. And hope that works. I think that's reasonable. Except for one problem, which is that almost always to make, in an inexpensive way, ruthenium complexes, you need to start with ruthenium-3, trichloride. So with that piece of information, what do you think? Tanner?
You heat that with 50 silver, PF6, and maybe an ethanol or a little bit of trichonyl phosphate.
Okay.
And you'll either ethanol and or trichonyl phosphate will reduce to ruthenium-2. And then halide abstraction.
So let's draw this in 2 steps. So indeed, this is essentially what's done. In the original paper by Burstall, they actually just used bipyridine itself as a sacrificial reductant. So bipyridine will homodimerize, and in that way can be a sacrificial reductant. And what they use in more sort of modern, tried and true preparations is to use have this written down somewhere. Which at first glance looks like it might be a P3, a P5 compound, but is actually P3 because of the tautomeric form. Yes.
Here.
Yeah.
Do people with ruthenium have to use silver? Because I know with iridium, you can just run it in water, and the iridium salt will crash out, and then you just filter off like ammonium chloride. You just use ammonium PF6. Do you know if people can do that with ruthenium?
It's a good question. I think that can be done by just playing with the salt, the solubilities. I don't have a definitive yes/no answer, but I think likely yes. So yes, Hannah's pointing out if we don't want to use this expensive silver salt, some other form of PF6 will probably get the job done. Very good. Anything to drive salt metathesis there? Okay, good. Any questions on that? Okay, so let's now discuss. So basically, we'll use Rubpy as kind of the the case study for thinking about some of these overall reactivity trends, because I think as you go across this series of different Rubpy derivatives and related iridium 3 complexes, that the story is quite similar. And so here's the structure, of course, of Rubpy +2. Upon photoexcitation, there's a metal to ligand charge transfer. So in general, photo-induced electron transfer is a reactivity paradigm where a donor molecule, upon excitation, transfers a high-energy electron to a low-energy LUMO on an acceptor molecule. And of course, these two moieties can be transferred or can be tethered together, so that this can happen intramolecularly. So the overall process is the same whether you're talking about an organic dye, an organometallic photosensitizer, et cetera. And so in this case, the electron-rich moiety is the metal center. The electron-poor moiety is the bipyridyl groups. And so upon irradiation with light, an electron from the metal can be transferred to the ligand. I've drawn this here in kind of an extreme form to just drive the point that now the metal becomes oxidized and more electron poor, a better oxidant, and the ligand becomes reduced and thus a better reductant. And so this form of it, of the excited state form, which you can view this way, will be abbreviated like this through the rest of class. And so in terms of the MO diagram, here's a simplified depiction of what this looks like. In the case of the hexacarbonyls, where we did not have low energy pi star orbitals, we drew this excitation to the sigma star orbital, but now we have low energy pi stars on Bipy. And remember, Vincent said that we have an octahedral complex that's D6. And so in the octahedral form, we draw this way with EG and T2G. And then because there's a low energy pyridyl ligand in this case, there's a pi star orbital that's actually lower than the EG. And upon irradiation, now we get metal to ligand charge transfer, intersystem crossing, and now we get a long-lived excited state where the pi star orbital of the metal is singly occupied. And so what's often quoted about these types of energetic intermediates is that they're both stronger oxidants and stronger reductants than the ground state. And so we'll see that as we go throughout the talk today. And so some of the advantages, you'll see now in the literature people using organic dyes and metal-based photosensitizers. And historically, I think the reason why the metal-based ones sort of caught on and really took on a life of their own in the end of the 2000s is that they have much longer excited state lifetimes, and that they have much better chemical stability compared to most of the organic dyes that were being used at that time. And so here are some of the metrics in terms of Rubpy specifically, if you're interested in its absorption, extinction, lifetime, et cetera. And then For those of us who think a lot about single electron transfer, either from an electrochemical perspective, or redox perspective, et cetera, here are some numbers to quantify how strong of an oxidant or reductant the excited state through Rubpy 2+ star is. So in photoredox catalysis, what typically happens is after visible light irradiation, 452 nanometers, then we encounter this intermediate that I've been, this excited state that I've been talking about. And now from here, we can take advantage either of its oxidative properties or its reductive properties. And so there are two pathways that can then take place. One is called oxidative quenching. So in the case of oxidative quenching, the ligand-based electron is transferred to typically an organic oxidant in solution. And then the other possibility is reductive quenching. Where an organic reductant in solution now is reducing the metal to the +1 oxidation state. So some common reductive quenchers, I'll just list a couple, and then you will have on one of your handouts, you'll have a sheet that has a much more comprehensive list of common reductive quenchers. And then oxidative quenchers. So this is easy to remember. Things that are good oxidative quenchers are oxidants, and things that are good reductive quenchers are reductants. Historically, a very commonly used class of reductive quenchers are these biologens. So just in case anybody is not familiar with this class of oxidant, I'll draw it. there's the doubly alkylated bipyridyl reagents. Okay, so now with this as a general framework for thinking about what's going to happen with a bunch of organic reagents upon irradiation of Rubpy in solution, let's take a look at problem of the day number 2. This is an example, early example from Corey Stevenson's group. And at the bottom right of the under the reaction arrow, it should be H nu. Didn't get the symbol font there. Sorry about that. So take a look at this. Sketch out a mechanism. Compare what you've got with your neighbor, and then we'll go from there. Any thoughts here to get us started? What do you think, Kai?
I'm not sure, but I think the linear maybe take one vector from the right compound, and the radical will attack the alkyne, and the ring will come close to the jet. Something like that.
Okay. So what is the compound on the right named?
I don't know.
Anyone want to jump in? There's a Hainchester. So more often than not, what are Hainchesters used for in organic reactions? As a hydride source. Yep. Okay, so we have Hainchester. We have as a reductant. Is there anything else in solution that can be a reductant?
Unix base.
Unix base, okay. So let's go ahead and get started just by seeing what will happen first. Okay, so we have Rubpy. Radiate with light. I think here everybody should go this far. Excited state. And now we just listed two reductants that we have in solution. So that could stand to reason that we are operating in a reductive quenching mode. So now one could invoke the Hainchester serving as the reductant here. I'll just tell you this wasn't right on the problem, but in the paper the Hainchester is not needed for many of the examples. So they often were able to replace the Hainchester with formate, which is less expensive. And so because the Hainchester is not necessary, let's draw the Unix base as doing the business end of this. So if we invoke single electron transfer of the non-bonding electrons from the amine base, then we will take advantage of the fact that this is now a better oxidant than the ground state, and this is essentially doing single electron oxidation of Unix base to itself become in the reduced form. So now this is going to need to get reoxidized by something. So now we have this radical. So in reality, let's just draw this as the Hainchester complex, or the ammonium formate complex. So with okay, so now do we have anything that is oxidant?
Substrate.
The substrate? Okay. What part of the substrate?
Carbon chloride.
Okay. So if this catalyst now engages this substrate, let's say it's by a halide or halogen abstraction mechanism, then we'll get chloride minus. The catalyst will be back in its parent oxidation state. We'll have an alpha carbon-centered radical. And now what's the ultimate fate of this amine base? This is going to essentially generate corresponding aminium and H dot equivalent. And now the substrate can do one of two things. What or what?
6
It can undergo, okay, it can do three things. It can undergo two different types of radical cyclization.
And recombination with hydrogen.
And recombination with hydride, or what's the other thing it could do? Okay, it could do four things. Homodimerize, undergo radical cyclizations, or what? Or what is
Get oxidized or reduced.
get oxidized or reduced? Okay. 5 things. Okay. Or it can react directly with the H dot that's generated in this process. So I think in the absence of more information, you could draw a lot of things. I think probably immediately you'd think about the radical cyclizations, and I think the reason why they actually highlight this example is that unlike the tin hydride chemistry that undergoes radical cyclization here, you're able to trap this radical effectively enough that you can get the reduced product without radical cyclization. So that's the point of this example in the context of this paper, but of course you wouldn't know that without seeing it. So yeah, if you proposed a radical cyclization, that would be reasonable as well. Good. Are there any questions on this?
So what's the function of interest? Yeah, that was my same question.
Yeah, so as I said in the paper, they did many of the examples with formic acid as the reductant. I didn't actually draw the Winchester structure here. So I think that my understanding is that it was an empirical observation that in this case it was better, even though most of their examples were done with the formate. And I think with the formic acid, it's perhaps a little more obvious because you can imagine that this actually is forming a complex. And you might convince yourself that this is a stronger reductant or kinetically a more appropriate reductant for this cycle than either of these reagents in isolation. In the case of the Winchester, yeah, I'm not sure. It could be.
To quench the aminium, like the aminium floating around in solution stoichiometrically can do bad things. So if you have single electron transfer from something that then becomes inert, right? In either case, that's what that's probably doing.
Or hydride transfer.
Yeah.
Right. Yeah, so Hannah's pointing out that the Winchester can serve as a good hydride donor, as a quencher of the aminium. That's reasonable as well. And then the other possibility would be that in terms of this particular example, perhaps you need this is a hydride source to outcompete this equalization, something like that. Those are some ideas. Good. Any questions on this one? Okay, let's go ahead and jump straight into problem of the day number 3, because I think it's sort of related to this discussion that we're having. So take a look at that. I think this can be a pretty quick one. 3 complexes, all related to Rubpy, and upon photoexcitation, which of the 3 do you think would be the strongest reductant, which would you think would be middle of the road, and which would you think would be weakest reductant? Okay, what do you think, Hansel?
I think the third one is the highest reduction.
Okay, so you're going the third one, so the right one is the highest, then what?
Yeah, reduction, in terms of reduction.
Yeah.
And second,
And then the second one,
yeah,
middle, and then left. Okay, does anybody get anything different from that? Okay, this is actually on your handout, so I'm going to cheat by, So if you look at this handout where the title is Table 1, it has the reduction potentials of several different compounds. And so, let's see, the 3 in question here are entry 4, Rubpy, entry 4, the phenanthrene analog of Rubpy, entry 3, Rubpy itself, and then I think the compound on the right is Rubpy BPM. Bless you. So the general trend is that electron withdrawing groups on the arene make the excited state more oxidizing. And of course, the opposite is true. Electron donating groups make more reducing. Good. Any questions on that? So if you look at Table 1, it also introduces another family of complexes that have emerged as being very important in photoredox. And so these are the these iridium-3 complexes of the general type shown here. And so the first thing to notice there is that these are cyclometylated through carbon. So these are CN bidentate ligands. These are typically abbreviated PPY. You'll also notice that some of these iridium complexes are heteroleptic versus homoleptic, meaning that they have 2 or more different types of ligand. And one of the most reducing so this is the big guns when you really need to high reduction potential for your substrate of interest. So remember we saw that introducing electron withdrawing groups sorry, I said that more reducing, more oxidizing. Electron withdrawing groups make them more oxidizing. And then I think these, from talking to people in this area, the fluorine and CF3 substituents have the added benefit of making the ligands a little bit less susceptible to potentially competitive Minsky-type chemistry that can take place with many of the radical species that are thusly generated. Oh, sorry, I really messed this one up. So these iridium complexes are associated with larger homolumo gaps. Higher energies of light are typically needed. And in terms of comparing iridium-3 versus ruthenium-2, ruthenium-3 tends to be better at stabilizing this heteroleptic ligand set that you see in this case compared to ruthenium-2. And there's also better what's called spin-orbit coupling, and that improves metal-to-ligand charge transfer. And so I think the point for end users is that now there's a nice spectrum of photocatalysts, including the transition metal-derived photocatalyst as well as the organic dyes that you can go into, look at your target transformation, and dial in the wave-light of length that's used, and hopefully get a predictable outcome in terms of the oxidation or reduction potential that's generated, just like one might do with electrosyn, where you can program in how reducing or oxidizing you want conditions to be. So let's see. With the remaining time, I'll just highlight what I think is a cool example of this same type of reactivity, but outside of traditional organic chemistry. And so this is some work coming from the Hawker Laboratory. The lead author in the initial publication was Brett Fors, who's now assistant, or perhaps recently promoted associate professor at Cornell. And so here, the authors cleverly took advantage of the spatiotemporal control that is provided by light for controlled polymer synthesis, and really took this into some interesting directions. I bring this up because for folks in the audience who may be considering doing postdocs in other areas, one of the big advantages that light gives you as a stimulus for triggering reaction is that it's the best input in terms of spatiotemporal control. So in terms of getting the types of reactions I've shown previously, there are other ways you could think about doing this. You could have chemical oxidants, you could have electrochemical oxidants. But there's nothing that beats light in terms of being able to pattern it and being able to control both the area that's irradiated and how long it's being irradiated. So the Hawker Laboratory developed this what's called photo ATRP. Normal ATRP is atom transfer radical polymerization. Chris Matuszewski and Sawamura are credited for developing this mostly with copper and also with ruthenium in the early days. And so in organic papers, you often see these light-dark cycles, and they're in the mechanistic section because it's probing that it's establishing that the reaction requires light to run, and that when there's no light, it stops running, and that can rule out like radical chain processes. But here, it's actually essential for the applications that they're using. So, for example, you can have a surface where you attach alkyl bromides, and then you put on top of the surface a photomask. And as you irradiate, only certain alkyl bromides, or I should say only certain catalyst molecules in proximity of some of the alkyl bromides are absorb light, and as a result, the polymer only grows in the areas where the photomask lets the light through. And so you can imagine this is a fairly straightforward way to do what's called lithography, patterning a surface with a molecule of interest. And so mechanistically, the way that this works, I'll just draw a simple cycle. So use radium-3. So here, iridium-3, remember we said is pretty highly reactive. And so this can potentially react directly with the alkyl chloride. So the alkyl chloride is an initiator, of course, and then so let's walk through mechanistically what's going on here. So iridium-3 is photoexcited to iridium-3 star. That can react directly with the alkyl bromide substrate, the initiator, or the propagating polymer, which also will contain an alkyl chloride. That generates this radical, which can then undergo controlled addition into alkene in solution. So this is the alkene, this is the initiator, this is the growing polymer chain, which of course has an alkyl bromide at the end. And then the iridium-3 bromide now just needs to get, let me see if I draw this right. It's okay. It needs to be reduced to turn over the cycle. Oh, sorry. I drew this wrong. The iridium-5 bromide recombines with this propagating polymer. Is that clear? So the iridium-5 bromide can recombine with this radical to generate the alkyl bromide in the growing polymer chain. It should be 4. Sorry. I drew 4 and then I said 5. Okay, so now with the remaining time, let's take a look at a couple examples, 1 or 2 examples of important photomediated reactions from the recent literature, and not necessarily fall under the umbrella of photoredox, but I think are important and illustrate some of the same reactivity trends that we've seen in today's class. So let's take a look at problem of the day number 4. So take a look at that problem, discuss with your neighbor. While you're doing that, I'm going to jot down a few references of reviews for the photoredox in organic synthesis. think there's Z Shi.
I think it probably promote the oxidative addition.
Okay. How does it promote oxidative addition?
I'm not sure, but I think first the cobalt is activated by light.
Okay.
The phenyliodine is reduced by the activated cobalt species.
Okay. I like what you're saying so far.
And generate the iodine anion and the phenyl radical.
Okay.
And the phenyl radical combined with the cobalt, the copper, and then do the reduction reaction.
Okay. Great. Anybody get anything different? Shout it out if so. Okay, so this is an example from collaboration between Greg Fu and Jonas Peters. Some people probably recognize it immediately. The development of the so-called photo-Ullmann. Classically, Ullmann chemistry requires very high temperature forcing conditions, and so the innovation here was to find by use of light, they could run these reactions as low as minus 40 degrees. It's pretty remarkable if you think about it. And so for those in the audience who attended Tianning Diao's recent lecture, you'll remember that even within the general realm of saying something's proceeding via an SET, oxidative addition, there are many different subtypes of reaction mechanism that can be operative. And so here there are, let's say, two, the authors say there are two main possibilities. So in this case, you have a electron donor. So this is a donor atom. And you have an electron acceptor, which is the aryl iodide. And you have photo-induced electron transfer. So people used to use this term quite broadly, PET, photo-induced electron transfer, but it kind of fell out of favor because PET also has another meaning, which is the PET scan. So I think this creates some confusion. So then people don't use this as commonly in the literature. Now, this would be an example of a PET process, photo-induced electron transfer. So the authors found that this copper complex has absorption bands that can be accessed via fairly high energy light. I think in this case they use this particular case I think they use a CLT, but in some examples they've used mercury lamp. And so we get a single electron transfer from the copper amido complex to the aryl iodide and subsequent oxidative addition that can happen in two ways. So one is that you get outer sphere SET first to make the iodobenzene radical anion, and then the copper, I didn't draw copper, that would help, copper radical cation. Then this homolyzes to here and then recombines, and then you get reductive elimination. Or it can proceed via direct halide abstraction, which I've shown here, to make the aryl radical directly, which I think is what you proposed, Zishi. Is that right? And then CN reductive elimination believed to happen via sort of a classical pathway. Are there any questions on that? So let me just show an example that I think is interesting. I know we're a little bit out of time, but this connects to so I think most people in the audience will have seen Teshik Yoon's this DLS lecture. And I think one of the interesting projects that he presented on was in his project on triplet energy transfer. And this is somewhat distinct from other examples of sort of photoredox that you see in the literature, where you get to this intermediate that's both a stronger oxidant or a stronger reductant, and then you use it either as an oxidant or reductant. But what the Yoon group has gotten interested in is taking advantage of this triplet state. So this is the triplet donor excited state, and you can react with a singlet, an acceptor molecule in the singlet state, and what happens is that one electron goes here, another electron goes here, and you can get triplet energy transfer to generate what are essentially diradical intermediates directly onto organic substrates. And so I'll just show one quick example. So one of the difference you'll see here is that based on what I had just said, there's no oxidative quenching, reductive quenching process. The energy from the triplet state gets directly transferred to the substrate, which then reacts. And so the example here is this Lewis acid activated, this is a chalcone derivative, scandium Lewis acid. And so, conceptually, this is a diradical, triplet diradical, and it then directly can generate diradical onto the substrate, which I think is really cool. And then this can react with an acceptor alkene to give 4+2 products with high EE. And so it's cited as one of the examples, very few examples of being able to engage photoexcited states in asymmetric catalysis, because remember, normally they're very short-lived, and the key to success is that in the absence of Lewis acid activation, this is a chiral Lewis acid, in the absence of Lewis acid activation, this is not a good triplet energy transfer substrate. Only upon Lewis acid activation, you have a chiral Lewis acid, can this participate in the triplet energy transfer. And so that's the key to high EE and having no background reaction. They published several nice papers on this. And so part of the point of emphasizing these last couple examples is that there's a lot of cool opportunities where you can take advantage of photo excitation of metal complexes, not just to do SET, to do reactions that you could do with other radical processes, but to actually do mechanistically unique processes as well. And so I've included a few references here. These are reviews from Corey Stevenson, Teshik Yoon, and Dave McMillan, respectively, on the use of transition metal-based photocatalysts. I'd also direct you to this book chapter from 2 decades earlier on organic dyes as PET compounds. So this should be available in your Canvas page. And I think it's cool to read through and think about what was being, what folks were working on already in the early 90s and what the limitations of that were and how the transition metal-based approaches have addressed some of those. So I think that's it in terms of lectures. So as I said, please let me know if you have any questions on the exams, and thanks for being a great class. It's been fun teaching you, and good luck. Next, from the TA.